picture this. A rover sitting in near-perfect silence on the far side of the moon, where Earth never rises and the radio noise from our planet fades into a faint hiss. And now, China has released a new set of mission images that pull us right down to the surface into one of the most mysterious places in the solar system. Before we dive in, if you enjoy space missions explained in plain professional language without the hype, hit like and subscribe to CosmoQuest 88. It helps the channel, and it tells the algorithm you want more deep space stories from lunar landers to asteroid probes. These images come from the Chang'e 4 mission, a true milestone. In the first days of January 2019, a Chinese lander and its small robotic rover, Yutu 2, also called Jade Rabbit 2, achieved the first ever soft landing on the moon's far side. Not a flyby, not an orbit, a landing with wheels on regolith. The touchdown happened inside the von Kármán crater, which sits within the South Pole Aitken basin. That basin is huge, one of the oldest and deepest impact structures on the moon. In simple terms, it's like a gigantic scar, and scars can expose layers you normally can't reach. That's why scientists care. The rocks here may carry clues about the moon's early crust and the violent impacts that shaped it. Let's clear up a common myth right away. The far side is not permanently dark. It gets the same sunlight cycle as the near side. It's far only because the moon is tidally locked, meaning it rotates once for every orbit. So from Earth, we always see the same lunar face while the opposite hemisphere stays hidden. Landing there is difficult for one big reason: communication. From the far side, you can't talk directly to Earth. So China solved the problem by launching a relay satellite called Queqiao. It sits in a special region of space where it can see both the far side landing site and Earth, acting like a lunar Wi-Fi tower in deep space. That single engineering step, building a communications bridge beyond Earth orbit, is a preview of how sustained lunar exploration will work in the future. Now, what do the newly released images show? We see the lander from the rover's point of view, and we see a surface that looks rugged and heavily processed by impacts. Small craters everywhere, sharp rock fragments, and fine dust, what we call regolith. There's no wind to smooth it, no rain to wash it. The landscape is shaped mostly by impacts, thermal cracking, and billions of years of micrometeorites that slowly grind rock into powder. Some of the most striking panoramas were assembled from the rover's camera views, including wide scenes where you can pick out the lander sitting like a small, bright machine island in a sea of gray. A nice detail here. Independent experts have also used public mission imagery to stitch together panoramas, helping the wider community study the terrain and rover tracks. Why does the far side look so different from the near side? From orbit, the near side is famous for its dark maria, ancient lava plains that fill big basins and create smoother terrain. The far side has far fewer maria and is much more cratered. One leading explanation is that the lunar crust is thicker on the far side, making it harder for molten rock to reach the surface in the past. Another factor could be the uneven distribution of heat-producing elements, which affects how much volcanism happened long ago. That's where Yutu 2 comes in. The rover isn't just a camera on wheels. It carries a panoramic camera, a mineral-detecting spectrometer, and a ground-penetrating radar that can see beneath the surface. The spectrometer helps identify minerals by analyzing how they reflect sunlight. The radar sends radio waves down into the ground and reads the echoes like an ultrasound for the moon, revealing buried layers. Those layers matter because the lunar surface is not one uniform blanket of dust. It's stacked history, ejecta from impacts, melt sheets, fractured bedrock, and mixed regolith. If you can map those layers, you can reconstruct what happened, how many impacts, how intense they were, and how they reworked the ground over time. Chang'e 4 also carried instruments for space environment measurements. One example is a radiation detector designed to track how energetic particles behave on the lunar surface. That kind of data isn't just academic. Radiation is one of the biggest risks for future astronauts and long-duration equipment. If you want humans to work on the moon, you need to understand the radiation environment in real conditions. There's another big scientific reason the far side is special: radio quiet. The moon blocks the constant radio interference coming from Earth, everything from TV broadcasts to radar systems. That makes the far side an excellent location for low-frequency radio astronomy. In other words, it's a natural shielded platform for listening to faint cosmic signals that could help us study the early universe, the birth of the first stars, and the evolution of galaxies. And then we get to the headline that sparked curiosity: the strange substance spotted by Yutu 2, described at first as gel-like. That word lit up the internet, but the scientific story is both simpler and more fascinating. On the moon, gel-like usually means glassy. When a meteorite hits at tens of kilometers per second, it can melt rock and regolith instantly. That molten material cools fast and can form dark, shiny glass. In this case, researchers describe the material as an impact melt breccia, broken fragments fused together by melt, producing a glossy dark mass on the crater floor. Reports suggested the patch was on the order of tens of centimeters, roughly the size of a small paving stone. Under certain lighting, glassy surfaces can look unusually smooth and reflective compared to dusty regolith. But composition matters more than appearance. The analysis indicated the material was not radically different from the surrounding soil, which supports the idea that it formed locally from the impact-heated surface mix. So, the mystery isn't that the moon suddenly has something wet. The mystery is the process: what impact made it, how hot it got, how the melt flowed, and what it tells us about the local geology. Each impact melt deposit is a natural experiment, frozen in time. Now let's talk about what the radar can reveal, because this is one of the most underrated parts of the mission. Ground-penetrating radar can detect boundaries between layers, different grain sizes, rock fragments, and buried blocks. In some cases, it can map structures down to a few tens of meters. That may not sound deep, but on the moon it's enough to see multiple chapters of surface history, like reading several pages at once instead of one line. And here's a performance detail that matters. Yutu 2 has operated far beyond its original design life. The lunar environment is brutal. Days are hot, nights can plunge to extreme cold, and dust sticks to everything. Each lunar day is about 14 Earth days of sunlight, followed by about 14 Earth days of darkness. Keeping electronics alive through that cycle is a serious engineering challenge. Every extra month of operation is extra science and extra experience for future missions. So what has China really found on the moon? Not aliens, not secret structures. What it's finding is something far more valuable: reliable capability and hard data. It's testing long-duration surface operations. It's mapping terrain in a place never explored by a rover before. It's studying mineral signatures. It's measuring radiation. It's probing underground layers. And it's doing all of this while proving that communication, navigation, and rover survival can work on the far side. That matters because Chang'e 4 is not a one-off stunt. It's part of a step-by-step lunar roadmap. Earlier Chang'e missions mapped the moon from orbit. Later missions learned how to land. Sample return missions aim to bring lunar rock and soil back to Earth, where laboratories can measure isotopes and microstructures far beyond what a rover can do. Each mission builds the next: better guidance, more autonomy, stronger communication links, more robust power and thermal systems. Now, quick mid-video question. If we build a radio telescope on the far side, what should be its top priority? Listening to the cosmic dark ages, studying Jupiter-like exoplanet radio emissions, or tracking solar storms with unprecedented clarity? Drop your idea in the comments. Your answers often shape the next episode. Looking ahead, the far side is also a strategic test bed. If you can land there, keep a rover alive through repeated lunar nights, and send high-quality data back via a relay satellite, you can operate almost anywhere on the moon. Combine that with future interest in the lunar South Pole, where permanently shadowed craters may hide water ice, and you start to see why the next decade could be the most active lunar era since Apollo. And there's a bigger theme here that connects to asteroid missions and impossible journeys. Space exploration is increasingly about infrastructure: relay satellites, navigation networks, reusable launch systems, robotic precursors, and eventually habitats and power stations. The quiet images from Chang'e 4, rover tracks, a lander, a cratered plane, are small signs of a much larger shift: the moon becoming a working destination, not just a distant target. So yes, the newly released Chang'e 4 images are, on the surface, simple: rocks, dust, craters, machines. But in meaning, they're enormous. They show sustained robotic presence on the far side, and they hint at what comes next: more landings, more sample returns, and eventually more ambitious missions that push deeper into the solar system. If you want more stories about lunar science, asteroid probes, and future extreme myths,